Okay, team, we're going to go over the in-class lab. Number 5, time of concentration. This is an assignment on Canvas. You can download the time of concentration Excel spreadsheet right here. And what we're going to do is calculate time of concentration using a 3 times kind of 3 components of water flow in a watershed. And then we'll compare that to a calculation that StreamStats actually makes. In Colorado, time of concentration has been implemented in StreamStats. We'll have a short write-up. Please upload a document separate to the spreadsheet where you have some paragraphs describing each step, what was accomplished and what the answer was. Please include appropriate equations, figures, tables, and captions. And then finally include a map of your watershed showing the 3 different flow paths drawn in there manually. This would be a nice kind of summary and documentation of all the steps associated with the time of concentration calculations. So I've gone and downloaded the spreadsheet. And here it is. Here's the documentation for the TR55 method. And we've got a section for each of the types of flow paths. The sheet flow, which ranges from 100 to 300 feet at the top of the watershed, shallow concentrated flow. And this is a line that essentially you calculate or trace to the first visible channel in your watershed. And then finally, we do channelized flow. And this is going to be based on parameters that you estimate from your watershed, from the channels in your watershed of interest to the outlet. I've given you all the appropriate documentation from TR55 manual here, so you can reference these tables. I'm going to go ahead and copy these coordinates, and we're going to go to StreamStats and include that in there. So let's just go back a step here. Paste those coordinates in. And it brings us to Colorado. We'll select Colorado. And I've selected a stream, these coordinates. You're welcome to do a different watershed if you want, but I've selected these coordinates for a relatively small watershed to do the calculation. I like to use the national map for my base map. This is going to have some topography and a little bit more information. That's helpful. It also allows us to zoom in a little bit more. All right, so let's zoom in and click on delineate and delineate our watershed. So this is basically draining to C.5 road. So you can imagine we're designing a culvert or bridge for C.5 road for this project. Now that I've delineated the watershed, you can see its extent right here. It goes up a decent amount. Now, from here, we can go ahead and continue and calculate some basin statistics in StreamStats. That'll give us our time of concentration and other basin information that we might use later, such as the curve number and other things. And there's a lot of information now that's been, or kind of models that have been implemented in StreamStats for Colorado, as well as Mesa County specifically. I'm selecting a few scenarios here. So peak flow statistics, flood volume, and then bankful channel statistics. And then we'll go down here to basin statistics, and let's just go ahead and select all these. It's going to be some redundant or information that we don't need, but we'll go ahead and calculate everything for the basin. So these are various climate, soils, time of concentration at the bottom, and go ahead and press continue. Now that the basin characteristics have been calculated, I pressed continue to generate this report. And we can just go ahead and go to the bottom, and we'll print it out as a PDF and save it. So we'll come back to that in a little bit, but might as well, while we're here, just look at time of concentration, and it estimates it to be 2.2 hours. We could probably look at StreamStats documentation to figure out how they do that, but it's probably going to be some rough methods similar to what we're using in class right now. All right, so now that we've got that information, we've saved it, we'll come back to it in a minute. Let's look at some exploration tools that we have. So in the top corner, next to this ribbon here, we have exploration tools. We can measure, we can do elevation profiles, we can do flow paths and traces. And so these are tools that might be helpful for us in a minute. Let's go look over here at our spreadsheet. We have our sheet flow, and we're going to calculate what our sheet flow is for either 100 to 300 feet. Now, I see a relatively not too steep. If we kind of look at the basin here, the contours are pretty flat, kind of like a mesa. So let's go ahead and measure and see how far we get. And we want to start at the most hydrologically distant point. And in this case, if we kind of look at our watershed, I'm going to go ahead and say that the very kind of distal tip of our watershed will be that hydraulically distant location. You could imagine that there's going to be some overland flow paths that could be pretty long until you get to a channel. So perhaps something like this, where you have a flow path that could take a while to get to the channel. However, because it's kind of long, we're still have to account for, even if it's fast flow in the channel, there's going to be probably some longer time. If you were doing this for a consulting project, you might go ahead and calculate a few flow paths and see which one ends up being longer in terms of time. So maybe start for here and kind of go over a really flat area before you get to a channel, and here, etc. But we'll go ahead and assume it's this, and I'm going to start here at the top, and I'm going to trace out 300 feet right there. All right, that's our 300 feet. Not very long, right? So actually, I might kind of do that again. Let's go ahead and measure. We'll start from the very tippy top, 300 feet. There we go. Okay. So that's our feet, but we need to get the slope. So let's go ahead and do an elevation profile. We'll select the finest EM resolution that we have. And then it says click the map to begin. So we'll just kind of remember approximately where we were. All right, so when we click on this elevation profile tool, we will, let's see here, so we selected the finest, and then we'll click on this select profile points. And so we'll draw our line from here to about 300 feet. There we go. And then it says double click to end. It's going to go ahead and query and give us our profile. So we can just take the delta Y, delta Z over delta X here. So 300 feet. And then we go from 5129 all the way down to, or 5190, 5192 to 5190. So we can use this then to estimate our slope using the profile tool. So that'll be our slope over here. We can estimate the P2, so this is the 24-hour 2-year recurrence interval, or 50% annual chance probability. Our length will be 300 feet. And then this can come from NOAA Atlas 14. So NOAA Atlas 14. And we can navigate to that website and use that tool that we've used before to navigate to our location and get that 2-year recurrence interval for 24 hours. So it'd be this one right here for the point that we're interested in. So that'll go in inches. And then finally, Manning's N. Let's go ahead and bring up a imagery map so we can kind of see what's actually happening here. So we'll zoom out and we kind of see that we're in this kind of Mako shale type of setting. We'll zoom in. Do we see vegetation? It looks like there's going to be some kind of desert scrub type of vegetation. So let's go over here to our Manning's N table, to table 15-1. We know it's not smooth surface. Maybe it's going to be kind of more range type surface, so 0.13. The underbrush, I don't know how much underbrush is going to be out there, but this is where you might want to go out in the field and actually check this. So for this particular setting, we can go ahead and choose somewhere around, let's just call it natural type of condition. If you go out there and you see a lot of soil, then maybe we're kind of closer to this range, or we could kind of split the difference. But we'll go ahead and just call it range and put in 0.15 here for a Manning's N. So we've done I've kind of showed you the various data points that we need. Our slope we can calculate using the slope tool in StreamStats. Our precipitation we get from NOAA Atlas 14, and then we'll use this equation to then calculate everything, our sheet flow time in hours. Now we'll move down to the shallow concentrated flow time. And what we'll do is we might look at the imagery, we might look at the actual StreamStats grid as well. In this case, they line up pretty well. You can kind of see that we see an incipient channel forming right around here. So we'll trace our flow path. I'm going to go back to the national map. No, let's keep that imagery. And we'll continue measuring. So 300 feet was about right here. And then let's just kind of click and make our way to the channel. You can imagine a raindrop kind of following that type of path as it gets near the channel. So that leaves us with about 977 feet. So 977 for shallow concentrated flow. We'll use the elevation profile tool to calculate the slope again. So go ahead and click that, select your points, and then we can retrace the steps here. It might be nice to do this in an actual GIS where you get to make sure you're tracing over the same paths again. All right, so we'll continue our elevation 5190.25 down to 5177 over about 977 or 1,000 feet. So that's our slope. Our cover type, we can come over here to the table and stick with probably a similar cover type as before, where we can kind of say, okay, it's not row crops, nearly bare, untilled, western mountain regions. Maybe that's a good description right there. So Manning's N of 0.015, and here's our velocity equation. So there's that K value, 9.965, S to 0.5. So that's the equation that we'll put in for our velocity. So this is from table 515-3. So you use that equation for velocity based on slope. And then we'll use all the time equation then based on length, slope, velocity to convert that velocity to the actual time. And that equation is, I believe, it's going from basically velocity in feet per second to time in hours, incorporating the length. Now that we've done that, we're going to do our channelized flow. So let's zoom out. And we've got these channels. So the channels are going to be changing quite a bit. The first thing we want to do is trace the length of the channels. And so we said that our flow enters the channel right around here. So we'll go ahead and use that measure tool, and we'll kind of zoom in and out to trace our flow path. And I can kind of click and drag here as well. So we'll trace our flow path down and continue to do that. And you'll see the channel is getting a little bit bigger. You're welcome to break this up and try to estimate different channel widths and do this calculation kind of in parts. But for this exercise, we can probably just do it all at once. Kind of lump it together. I'm being pretty quickly here. You might take a little more time to try to get all the meanders in this channel. And we're almost there to the bottom. All right, so that's about 19,000 feet. I could have just done this with the slope tool, because that slope tool will give us the elevation profile, will give us the length as well as the slope, right? So that's something we could do all in one go. So go ahead and run that tool and maybe do the slope tool just from the tip of the watershed and trace it all the way down. So that'll give you, for the Manning's equation, that'll give you the slope parameter, which should be in here. Make sure we add that to the spreadsheet. But slope is in the Manning's equation, Manning's N, something that we'll want to pick from a table for natural channels. And then I'm telling you to say, okay, either assume rectangular or trapezoidal shape for the channel. And then we're going to assume that the flow is flowing at bank full. So that trapezoidal is full, that trapezoidal channel is full. Let's go ahead and zoom in. We can kind of pick a midpoint in the valley, and we can measure the width of the channel. I'm not zooming in super well. You might go to Google Maps and try to do this, but we'll try to get a rough width. This is a wash type of channel, so maybe somewhere around 15 to 20 feet. Then we can use that for the width. We'll say that the depth, again, you might go out in the field to actually measure these things, but we'll say that the depth is somewhere between 3 and 5 feet. And then we'll assume a one-to-one slope for the valley margins. So using those basic channel characteristics, you can go with the defaults that we have in the spreadsheet, or you can try to estimate your own remotely. Then we'll assume the channel's full. We'll calculate the area using the trapezoidal channel or rectangular channel equations, wetted perimeter, hydraulic radius. I gave you a Manning's roughness of 0.45. You could do something else if you think it's going to be more rough. For example, a vegetated channel that's like a wash with shrubs and grass inside would probably be a little bit rougher. And this should actually be 0.045. So with all that information, we can use Manning's equation to calculate the velocity using this equation right here. And so if everything is in feet, then we use the Manning's K value of 0.149. We put in the hydraulic radius, the slope that we just calculated, and that can be the average channel slope through the watershed. We'll put our length in here, and then with the velocity estimate, the length, we can then calculate the total travel time of water in the channel at bank full flow in hours. And so that'll just be converting that velocity to a time using the length to make sure we're going from feet to second to hours. So now that we've done all those steps, we can add everything up and get our time of concentration. Let's estimate and compare that to what StreamStats calculated in that report. And then I want you to do a quick write-up describing all the kind of parameters that you chose for each of these three components and what equations you used and data inputs, et cetera. So just kind of a one-page document of everything. Include a sketch. It can be a screenshot of your watershed with your sheet flow, shallow concentrated flow, and then channel flow paths included in that drawing. So that's a walkthrough for this assignment, and I look forward to seeing the work that you all do.